Let's get started. My name's Keith McQueen. I've been with Pyrofex since early December. Before that, I didn't know what R-chain was, and I didn't know what a blockchain was, and so I've been learning lots since then. I'm co-presenting with Timm Schäuble. Trying to get that right. We've been working in the Rosette virtual machine. The Rosette virtual machine was originally created by Greg and some others back in the early 1990s. It's a rather interestingly engineered piece of software. It does a lot of things. Primarily, it is a compiler for the RBL language mentioned by Henry, the Rosette base language. And Greg's here to keep us honest. Welcome, Greg.
Yeah, I'm sorry I missed Henry's stuff. I was being interviewed and I feel bad about that.
It's okay. So Rosette is a combination of a compiler and a virtual machine. It compiles the Rosette base language, RBL, down into byte codes. And then it executes those byte codes in the virtual machine portion of Rosette. Was something else you wanted me to say?
I think that was it.
Okay, that was it. Okay, let's dive in. Okay, Rosette is an actor uses an actor model. There are actors and objects within the system. So it starts out with an object called a context. A context contains a piece of code. It contains the data. It contains where the result of executing that piece of code is going to end up. It contains the arguments to the piece of code, and so it's kind of the basic piece that goes into the virtual machine. There is a thing called a strand pool. It's basically a queue of objects that are or contexts that are ready to be executed. They have everything they need. They're ready to go, and so that when that context time comes up, it's ready to go. It gets executed. A context can have children, so that there's a concept of nesting of these context objects. And each child context has a reference to its parent, so that when it is done executing, it can pass the data back up the line to its parent, so its parent can then be ready to execute. Let's see. And assuming that a given context, a given parent context has received all of the data that it needs to execute, then it may be ready to execute. So it may be scheduled. And so that happens when there are no outstanding, no unfinished business for that context. This is kind of what the internals of a context looks like. We have the program counter within the context piece of code, not the overall system, just within its own piece of code. We have an outstanding, and forgive me, I don't recall exactly.
It tells us how many arguments are left.
How many are left unfinished? Okay? We have a result and a target, the arguments, and then a pointer to the code, and a pointer to any parent context that this context may have. Starts out by installing a context that just basically creates it and gets it ready to go in the system. Now, if we dive into RBL, we have an example here that we've created to show how this system works. We're defining an operation. We're defining an actor. And then within that actor, we're defining a method called return one, and it does something incredibly complex. It returns one, as you might have guessed. And then we're creating an instance of that actor and calling it foo. Go ahead, Mike.
There you're defining an operation with the name return one and a method with the same name. Is that required, or is that just common practice, or what?
Greg says yes. We puzzled over that, Tim and I, but Greg says yes.
So think of the operation as like a key. So think of the operation as like a key, and that key together with the arguments go into the mailbox of the target, which is the actor where you're invoking where you wish to invoke the method, right? So that message arrives in the mailbox, and then at some point the actor's at a place where it pulls that message off of the mailbox queue, and now it says, okay, the key is return one. Do I have any method code that is associated with that key? So it goes down its list of methods. Here's one called return one, and then it invokes it.
Define multiple actors that use that same key? Or
yeah, and that's how you get polymorphism, right? That's the actor style, the actor version. So think of the operation as if you're familiar with Common Lisp, that's a generic function, and that's a multi-method. Yeah.
Okay. So we're going to start out by how an actor gets invoked. We're going to start with a simple example. We're going to call return one with a parameter of foo, and it returns one. Okay. Now we're going to step it up a notch. We now have two contexts. We have this inner one, which calls return one, and then we have an outer one which calls the addition primitive with a parameter of one, and whatever it would have been, whatever will be returned from this inner context. Does that make sense to everybody? Let's see. And of course, I got ahead of myself. Okay, and the end result we're hoping is 2, because we get 1 from return 1, we get 1 from this argument, and then we add the 2 together.
Okay, this way.
This is where Tim's going to take it and dive deeper. Yes, you can get the mic.
Okay, so now that we know some of the basics, we can look at what our example compiles down to, and it compiles down to this bytecode. And I'm going to walk you through the bytecode now. So log2 just creates an argument tuple which can hold 2 objects, and as you might have guessed, we need that to hold the 2 integers we want to add together. In the second step, we just put 1 into the first position of the argument tuple. Third step, here you have to know what the global environment is in the Rosette VM. It's basically just a store that can store all kind of objects, and here we just put a reference from the plus operation into the target register. I think it's called target register because everything in Rosette is an actor, and you send messages to an actor/target. That's where the name is coming from. Now things start to get interesting. Outstanding 12.1. What this does for the installed context, it sets the PC field, the program counter, to 12, and it sets the outstanding field to 1. And right now we don't understand why yet. I will come back to that. Push alloc1. What this does, it creates a new context and installs it into the VM. Has an argument tuple for one object, and important to note here is that it has the reference to the initial context, which is the parent context. So we just, in the previous step, created a new context, which got installed, and this new context basically represents the return one invocation. Here, pretty simple, we put a reference to the foo instance into the first argument tuple of the newly created context. Same here with return one into the target register. And now, what XMIT, the XMIT opcode does, in general, it dispatches the arguments to the target. The next here means that after the dispatching, we will return control back to the VM. That means that the VM then will go back to the strand pool and get the next context. The arg1 here means that the result of the dispatch will be written into the arg1, which is the second argument position tuple, write that back into the parent context, because that's where we want to have it. What also happens here is that we schedule another context which contains the bytecode of the return one method, which, as we remember, just returns 1. So in the dispatch, when we do the dispatch, at some point we will call this method. This, by the way, is how 20-year-old C++ code looks like. The important things here are that we here install, we got our initial context, and here we override the initial context, not the initial context, the second context we created. We get that here and override it here with the bytecode of the return one method. And we also set the program counter to 0. And here we schedule that context. So it gets appended to the strand pool. That means at some point this context will be run by the VM. And what then gets run is this. Let's ignore the first opcode, extend 1. It's not important for our example here. At the second position, you can see that we just put 1 into the result register and then call this opcode, the return opcode. What this does, it just returns whatever is in the result register to its parent context. And we set the parent context earlier to the initial context. then what return next also does is it schedules the parent context. And the next tells us again, or tells the VM again, that it should hand back control to the VM. Okay. So I just said that return next schedules the parent context, but is that always the case? No, it's not always the case. Here it was the case because the outstanding field of the parent context was set to 1 earlier. Now you can understand the outstanding opcode. Yeah, so the outstanding field, which gets set by the outstanding opcode, tells us how many arguments are missing in the parent context. Okay, so we just schedule the initial context again. At some point, the initial context will be picked up again by the VM and will run. And it will run at this position, at the 12th position. This is also why we had the 12 here, because we set PC to 12 there for the initial context. So we end there now. Yeah, that's basically what I just said. And then the dispatch function at position 12 will just perform the addition and gives up control to the VM. Yeah, that's it. Any questions?
Why did you have to set the outstanding to 12? What was that the number?
So there are two things. So there are two things there, right? One is the number of outstanding and where you're going to pick up control again.
Right.
Yeah, so the 12 is where you're going to pick up. Like it knows ahead of time, because it knows the layout of the bytecode, where to pick up the next instruction. That's what the PC is doing, is the next instruction.
Could it be any value?
Could have been wherever that landed. It could have been.
It's actually the 12 that's right there on the screen. Right?
Yeah, exactly.
Exactly.
The bottom line is the code.
Yeah.
Oh, it's telling you what line to look for.
Yeah.
Okay, sorry.
Yeah.
Thanks.
It may be slightly confusing here as far as the arguments. You can see that in this code segment, there's arg0 is referenced twice. Those are two different arg0s. The first one is the arg0 of one context, and the second one is the arg0 of the inner context, the child context. Yeah. Yeah. Just wanted to make that clear.
Thank you.
The plus gets invoked by XMIT?
By the last XMIT at position 12, yeah.
By the dispatch that's
Yeah.
titled by that.
Kyle?
On line 11, what is the arg1 next to the XMIT next?
It tells us, or tells the VM, where to write the result to in the parent context.
Okay, so where does it write the result for line 12 then?
Sorry?
Line 12 has an XMIT next. Where does it store its result?
It doesn't pass a result back in this case. That's why there's no
So it's thrown
target.
away?
Huh?
Yeah,
Yeah. In
It's
this case, yes.
the circular file.
Right, because that's the top-level expression, that it is essentially
Exactly.
the REPL is the thing that gets it.
Cool.
Just one comment here. The virtual machine itself, because we need to know about all of the Rolang code in order to do matching once something is transmitted, the compiled code is going to be used as a just-in-time, I'm sorry, the compiler here that outputs opcodes. The opcodes will be used in context where we're doing just-in-time compilation. And Kyle, I think you can say more about that.
So when you compile a row lang term, you can actually tell which parts will be data and which parts will be code. And we never turn the parts that will be code back into data. So you can compile it down, not just in time, but you can compile it down. But you're still going to have row lang that's uncompiled in there. And if you try and, there are specific syntactical constructs, and if you want, I can draw them on the board, where we evaluate things that were previously data. And at that point, you would have to just in time compile it. This one should be obvious. We have the ability to take a name and turn it back into a process and evaluate it. Hold on. This is very similar, except that we're doing the unquote on receive in the pattern. Similarly, if you use the nth method, you can pull a process out of a list. Lists have no side effects by themselves, but if the element here is a process with side effects, unwrapping it causes that row lang process to be actually evaluated. If you are familiar with interpreters, you can actually look through the interpreter and you can figure out, oh, when are the things that we're doing that where we actually evaluate something.
Is now a good time to tell the story, the C++ to Scala story? And does RBL stay forever or disappear? Or?
I'm not writing that story.
Mike, you want to talk about that?
So RBL is, as we mentioned, an optimization that we're going to be using. The RBL code right now is in the process of being translated. I'm sorry, the Rosette C++ code is in the process of being translated from 30-year-old C++ with all kinds of amazingly twitch-inducing optimizations. Things like taking a pointer, and then because you know everything is aligned on the 4-byte word boundary, hey, we've got 2 free bits, let's stick tag information in there. So it's not actually a pointer anymore, right? All these things that people thought were cool 30 years ago and amazing. And
they were cool.
So,
it was shoehorn what you got to do into.
Of course, yes. Who needs more than 640K, right?
Exactly.
So then there's not only that, but then there's the fact that it was all written as mutable state. And our task was to translate it into Scala where everything is purely functional. So Timm has done some amazing monadic things. I mean, consider this. Anywhere in the code, you can get a pointer to an object. But a pointer to an object is just a reference into this big block of memory. If you want to be passing state around, you either just need to make a big block of memory that you're passing around through all the code, or you need to, we started out by having a VM state object with fields and so forth. So at this point, then you have to be passing that around and turn the pointers into paths through this object so that you can update the entire state thing. Had we known how complicated this would have been, we would have pushed back a lot harder on Greg for doing this style of translation. I cannot give enough kudos to the VM team for the work that they have been doing on this translation effort. That said, this VM was always intended as a stopgap measure for something that had the right semantics for the concurrency story. In the future, we intend to develop a machine that is specifically tailored to Rolang, optimize the heck out of that, transition over to using that for compiled bytecode. So eventually it will go away. In the meantime, Roscala, as it stands, does not include the RBL compiler. So we're looking at the potential to split off the RBL compiler component, keep that in C++, and use the Scala implementation of Rosette. We're trying to do this as modularly as possible, trying to take chunks as they come. The RBL compiler is a significant component that would take a long time to do, so we're trying to get as much of this into the project as possible without pushing the deadlines back. So we still have the end of the year goal of getting this delivered. Did that answer your question? Sorry, Dan?
I think so. I guess a little bit more. So does the RBL compiler do any kind of modern stuff like constant folding and stuff like this that would make it much better than an interpreter?
Yeah, I mean there were a few tricks, right? The biggest trick is this context shredding idea, right? That was the main thing. It's like, so you have a lot of declarative information within Rosette about what's in sequence and what's in parallel, and so shredding the Rosette code down into a bunch of contexts is what it's really good at, and that sort of that's the abstraction that we want. That's the special sauce that we want as a kind of layer in front of the hardware architecture for now, right? Because there isn't any other abstraction out there that has been pounded on as much in a commercial setting that has the concurrency piece at this level, right? This abstraction of concurrency in front of the hardware, right? If you try to, like LLVM is the most natural thing to go for, but their concurrency story is just all wrong. And it's there we go.
So the shredded contexts, each one of those is a bit of serial code, right?
Yeah, that's right. So it's basically what the compiler does is it shreds the Rosette code down into little strands of code with dependencies amongst them. Like you saw the whole dependency management thing with the outstanding, right, and all of that. So that's what it's doing, is chopping up the code into little bitty tiny strands and then organizing them in terms of their dependencies.
And then there's this queue of contexts, and can you pick those off and run them in parallel? Where does the parallel?
Yeah, that's the idea. Is that you should. There are some caveats and gotchas in terms of our current implementation, but the whole idea of scheduling strands is that you should be able to pass them off to a thread in a thread pool.
Okay.
Yeah, that's the idea.
Is Graal interesting? Any of that stuff?
I don't know.
Oh, okay. It's a dynamic language VM stuff that the JVM folks are working on. So I've got a nod over here.
Yeah, I don't know enough about the project to be able to say. It is interesting.
I mean, the issue is like the JVM itself is just this giant beast, right? And we want to be a lot leaner and meaner. And get out to, I mean, wouldn't it be awesome if we had Rolang running in a toaster, right? That would be or on a watch. Yeah, exactly. So I think this would be really nice. And so we want to be as lean and mean as possible. Also, you know, the JVM's idea of concurrency is very heavyweight, right? Which is why people write these green thread libraries on top of the JVM for exactly that reason, right? So maybe we could just cut out all of that stuff and get closer to the metal. That's the hope, anyway.
Okay.
At the moment, we're not making full use of the concurrency that the that Rosette provides. Most of the asynchrony and concurrency that we're actually making use of at the moment is all tied up in the tuple space, the dispatch and the retrieval and all that sort of stuff. But we have plans for Venus on how to extend this and make more fundamental use of it.
Okay, that doesn't come through very much in the architecture. Well, maybe it does in the architecture document a little bit. But to say that the JVM is heavyweight and we want to get past it, and then to write all the code in Scala makes my head tilt a little bit.
Yeah, that's because. So the implementation is iterative, right? So we want to self-host. So once we get a working version, then we're gonna self-host and implement Rolang, the compiler, everything else in Rolang.
Okay.
Yeah. So then kick away the.
So we have needed code generation.
Yeah, that's the idea.
Who's running the Rolang compiler in Rolang? I haven't started that one yet.
What's that?
The Rolang compiler in Rolang?
Yeah, that's the idea. Everything, we should self-host. So we rewrite the whole thing in Rolang.
Any more questions? Cool. Thank you.